Okay, so today we're very happy to have Soubhik Koumar talk to us about hotspots on the CMB. Soubhik was a graduate student in Maryland, is a postdoc in Berkeley now, has been visiting us a few times over the last year, and he will be starting as a postdoc in the fall or late summer, I believe. So take it away, Soubhik.
All right. Yeah, thanks a lot for the kind introduction, and thanks for joining, and thanks for having me. So today I'm super excited to talk about hotspots on the cosmic microwave background, how these hotspots can arise, how we can look for them, and what we can learn about very, very high energy particle physics by looking for hotspots. So this will be based on a couple of papers written in collaboration with an excellent set of collaborators. So in the first paper, we elucidated some of the basic properties of these hotspots and devised some of the basic search strategies. And then in the paper from earlier this year, we developed some machine learning tools to look for these hotspots. Okay, so I'm gonna talk about basically these two papers. And I should clarify anytime something is not clear, just feel free to interrupt and ask questions. Sounds good. So, so we understand most of the phenomena that we observe in our universe in terms of four fundamental forces. There is the force of gravity, the strong force, ENM, and the weak force. And potentially, depending on the nature of dark matter, there can also be a fifth type of force that I'm just generically calling a dark force. Now, among all these forces, we understand the interplay between these three forces quite well, and that is thanks to the standard model of particle physics. In particular, we do understand that the weak force and the electromagnetic force, they are not really completely separate objects, but they're really part of a more unifying theory, namely the electroweak theory. And with the help of the LHC and various associated searches, as well as predecessor experiments, we generally understand standard model particle interactions quite well up to like energy scales of a few TeV or so. But from a particle physics standpoint, there are a lot of unknowns, especially as a particle physicist, we'd often like to know what is happening at energy scales much beyond a TeV. So there are lots of questions regarding that. For example, you could naively ask whether there are particles which are much heavier than a TeV, whether these particles they exist in nature, whether there are new symmetries that come into play at these very high energies. You can also ask classic questions like what happens to the dynamics of all these forces as you go to very, very high energies. For example, is it possible that all these forces they actually get unified into some bigger theory, something like a grand unified theory at some high scales? And finally, physics at high scale might also have some bearing on the nature of dark matter, which is something that we do not know a lot about. So with these questions in mind, and especially keeping the very high energy physics in mind, it's important to understand that we do have some very classic and concrete targets regarding what kind of particles could lie at very, very high energies. So I'm just going to talk about a couple of examples here very briefly. So famously, if we look at the coupling strengths of the electromagnetic force, the weak force, and the strong force, and if we extrapolate the coupling constants or the coupling parameters to very, very high energies, we see that given the running under the standard model, that all these forces, their coupling strengths, they become very, very close to each other around some very, very high energy scale, like of the order of 10 to the 14 to 10 to the 16 GeV. Now, these are fairly interesting and this potentially would have some very interesting implications, and this is highly non-trivial in the sense that you basically are plotting three straight lines, and a priori there might not have been any reason why these three straight lines they are coming so close to each other. But the fact that just within the context of standard model they are coming so close to each other, it basically gives a strong hint that all these three forces they can be a part of a bigger grand unified theory. And that has been one of the motivations for looking for grand unified theories using various probes. But of course, the challenge has been the fact that this new physics or the new particles that is associated with unification, they are really very, very heavy, like of the order of 10 to the 15 GeV or so. In a very similar vein, if you want to, for example, explain why the neutrino masses are so small compared to masses of other leptons in the standard model, then there's a classic mechanism, namely the seesaw mechanism, which can simply explain why the neutrino masses are so small. And it basically says that the smallness of the standard model neutrino masses, they are associated with the heaviness of some right-handed neutrino, and there is basically this inverse relationship which acts like a seesaw. So the larger the Mn is, the smaller the observed neutrino masses are. And then if you again like plug in some reasonable values for various Yukawas and Higgs webs, you find that for right-handed neutrino masses, again of the order of 10 to the 14 to 15 GeV, you tend to explain the neutrino masses fairly well. So the challenge for both of these setups is that the expected physics is taking place at a very, very high energy speeds, right? So that naturally makes probing these possible particles very, very hard. But that is not to say that we cannot probe them at all. There are famous experiments or famous probes like the proton decay experiments that can look for these very heavy states. But of course, the point is we cannot produce these so heavy particles in today's experiments. So you're always looking for basically their off-shell or indirect signatures. So this is where early universe can play a very interesting and unique role, because the early universe could have been sufficiently energetic. In particular, if you look at the inflationary Hubble scale, it could have been as high as 5 times 10 to the 13 GeV, which means that some of these very, very heavy particles, like particles associated with unification or right-handed neutrinos, they could have already been produced during this inflationary epoch. So then what we can do as theorists is that we can try to understand what kind of implications these very, very heavy particles can have if they are produced during inflation and if they leave their signatures in their decay products. So in other words, we have to understand their fossil records by looking at various cosmological observables like the CMB or the distribution of galaxies and so on. So that is going to be the broad theme of this talk. So we're going to try to understand how, by using various cosmological observables, we can probe very, very heavy particles that could have been produced during the early universe. Now, depending on the mass of the heavy particle, the associated phenomenology can vary quite widely. So just very roughly speaking, you can categorize the associated phenomenology in two parts. First, you can focus on particles which are, I'd call, somewhat light to somewhat heavy. So just quite arbitrarily, let's say if the particle mass is between like 1/10 of the inflationary Hubble scale, in between and up to like 100 times the Hubble scale. So as we'll see in a moment, if particle masses lie in this regime, they can typically be produced in sufficient abundance during inflation. And depending on their masses, they can give rise to a variety of phenomenology. For example, light particles produced during inflation, they can give rise to isocurvature fluctuations. Somewhat heavy particles, they can also give rise to oscillatory features on the power spectrum, which is something cosmologists are actively looking for. They can also give rise to oscillatory features in non-Gaussianity of density perturbations. This is something people study in the context of, for example, the cosmological collider physics paradigm. On the other hand, if the particle masses are even heavier, so much heavier than 100 Hubble, what happens is that you typically do not have enough energy in the inflationary background so as to produce these particles in a lot of numbers. So their production becomes much rarer. So you only have a few of these particles getting produced. But that has a couple of associated benefits from the perspective of phenomenology. For example, you can be in a scenario where you produce only a few very, very heavy particles, and that might give a chance to explain, for example, the dark matter abundance without overclosing the universe, because you're not producing a ton of these particles. But that is, of course, it depends on the model, and one has to go through the parameter space carefully to see if one can explain the dark matter abundance. The possibility that I'll be talking about during this talk is this one. The point is, because these particles, they're so heavy, after getting produced, they can actually back react on the space-time metric around their locations, and as a result, they can give rise to very, very localized features in position space.
Yeah, sorry. Yes. Yeah, I'm confused why this can explain gamma abundance. It seems if we do live some estimation, that's e to the minus 100.
I'm gonna talk about that. It's not as bad. I mean, in the sense that so you can pay some exponential suppression, but that exponential suppression is not enormous. But let me talk about the expression for number density in a few slides.
Okay.
But I should clarify, like, to really see whether this can be the dark matter, it does require a parameter space analysis, which is not going to be the focus of this talk. But I'm just going to illustrate the basic idea.
Thank you.
Okay, so we are basically going to see that very, very heavy particles, they would give rise to localized features in position space. So just as an illustration, we'll see that heavy particles, they can give rise to localized hotspots on the CMB sky. So if you're, for example, making a sky map, there will be certain locations where CMB would appear brighter than usual. So that's going to be the signature that we can look for, and by looking for these signatures, we would be able to probe particles which are much, much heavier than the inflationary Hubble scale. So that's the broad idea. So with that in mind, this is the outline for the rest of the talk. So first, I'm going to talk about how these hotspots arise. I'm going to talk a bit about inflationary particle production and how these very heavy particles give rise to hotspots on the CMB. Then I'm going to talk a bit about their properties. For example, how many of these hotspots we typically expect, what kind of shapes they have, and so on. And then finally, I'm going to quickly discuss about some of the search strategies you can adopt to look for these hotspots. So with that, let me start with the first bit over here. So I'm going to talk about the aspects of their production. Okay, so to discuss this, it is useful to recall that we have a couple of important scales during inflation. So first of all, again, we are interested in producing very, very heavy particles, particle masses that are bigger than, let's say, 100 Hubble. Now, we do have quantum mechanical fluctuations existing during inflation, and these have roughly sizes of order Hubble. So they are by themselves not enough. There is not a lot of energy in just the quantum mechanical fluctuations to produce these particles. But there is also a second scale in the problem, and to illustrate that, you can imagine that you just have the standard, some slow roll potential with the inflaton field rolling down on the potential. So in this context, if you just compute the power spectrum of density perturbations, this is the expression you get where the power spectrum is given by Hubble to the 4 over phi 0 dot square, where phi 0 is basically the homogeneous value of the inflaton field and dot denotes a time derivative. Now, just by fixing the observed normalization of the CMB power spectrum, you derive that phi 0 dot is a quantity that is 60 Hubble entire thing squared. In other words, the inflaton field, while it is naively slowly rolling, it is really slowly rolling with respect to the Planck scale, for example. But if you were to compare the rolling of this field with respect to the Hubble scale, it does have enough amount of like homogeneous kinetic energy. And this is a kinetic energy that you can potentially
turn off.
Yeah. Okay. Thanks. Sorry if I broke your. Okay, sorry about that. So what I was saying was that there is enough energy in the homogeneous motion of the inflaton field itself compared to the Hubble scale. And potentially, this is something you can use to produce these very heavy particles.
Soubhik, I'm a little bit confused about the numerics.
Yes, yes.
So P zeta is the
10 to the minus 9 or something like this,
Yes.
right? But shouldn't it be something like 600 then? Because 1 over 60 squared is not.
Yeah. So I
Oh,
have
wow.
omitted various factors of 2's and pi's and so
Okay.
on. So if you insert them all carefully, it's what you get.
You squared it twice, right?
Yeah, but even 60 to the 4th is not quite. Yeah.
Yeah, yes, there are some
2
factors
plus
I have omitted.
Sure.
Yes. Okay, so how can we produce these particles which are even heavier than this naive scale of 60 Hubble? So the idea is going to be the following, and this is something that people have considered, like this type of scenarios. They do arise in the context of more UV motivated models. The idea is the following. So we are going to imagine that this very heavy particle of interest is going to have a mass that varies with time. In other words, it varies as the inflaton moves along its own potential. And what I'm going to imagine is that the particle mass, it typically is pretty large, but then at certain instance of time, when the inflaton passes through some particular value, the particle mass, it basically passes through a minimum. And the minimum value of the mass, it is something of the order of this kinetic energy scale. And then following that instant, again, the particle mass can increase, and this is where particle production would be shut off because the particle is too heavy to be produced. So this is just going to be a toy model, but I should clarify that you can have in more complete models, for example, in this paper, what typically happens is that you can have oscillatory features on your inflaton potentials. So there can be multiple times where the inflaton field would pass through such minimum, and here I'm just focusing on one particular minimum just for simplicity.
Where does this minimum scale came from? Because if you're everyone, I think that particle may even turn tachyonic for some time. And
sorry, could you repeat?
Why is there this minimum for the mass? Where it's coming from? Because a priori I could think that okay, for some time it can even turn tachyonic.
Yes. That can also happen. So in that case, you'll produce even more number of particles. Yeah. So what I have in mind is, let's imagine you have like an m square phi square potential, but just some higher harmonics, also like some high frequency oscillations on top of this. Then as the inflaton moves around, you can have some particle mass which is like going through some minimum as a function of the phi field value. And I'm just choosing one particular instant of such case where the particle mass is varying with time. So I'm going to show you the coupling in the next slide, just an illustration. Okay, so this is going to be the basic idea. We're going to have a very heavy mass. So particle production would be shut off here and here, but this is where the particle mass would be close to the kinetic energy scale, and this is the time instant where particle production can take place. So let me just generically parameterize this. So this is just a very simple expression for the effective mass for these heavy particles, which I'm calling chi. And I'm just doing a simple Taylor expansion around the minimum. So you have the leading order term, and then there is a quadratic piece because the first order term vanishes. Now this looks a bit strange, so let's just simplify the notation. So I'm just gonna call this object parameter here m0 square. So this is basically the value of the minimum mass at the bottom of this curve here. This is some positive dimensionless coefficients. I'm just going to call it g squared. And this term over here, this is basically the field value for the inflaton when at time t star. So this basically controls the time of particle production. So if you just use this notation and if you rewrite phi star as mu over g, then the expression for the chi particle, for the effective mass of chi, it becomes much simpler. So what it tells us is that between the inflaton and the heavy field, there is a coupling which is g. This is the field value of interest, and this is the minimum mass that the chi particle always has. So in summary, what we are just imagining is that there is just a phi square chi square type coupling with a coupling constant of g. And just for completeness, we are going to focus on order 1 values of this coupling g, so that the loop corrections on the inflaton mass can be in sufficient control, depending on if the UV cutoff is not too far high compared to And again, this type of couplings, they would arise in more complete models. For example, if you have oscillatory terms on the inflaton potential, you can focus on like the value of those oscillations to effectively reduce the effective mass in this form. So just to summarize the story so far, we basically have three parameters. There's a coupling G that controls the coupling between phi and chi. There's this parameter M0 that governs the minimum mass here. And there is a field value mu, which you can also replace by the time of particle production. In particular, it is more convenient to use the size of the co-moving horizon at the time of particle production. So I'm gonna call that eta star. So these are the three parameters that is going to determine most of the physics of particle production. Okay, so just to give some basic intuition regarding how particle production happens during in a cosmological background, we can have this following cartoon in mind. So let's imagine that you have some harmonic oscillator and you have a particle which is in the ground state. So this is the wave function for the particle. So now what happens is that if you change this potential well in a non-adiabatic fashion, so if you just quickly stretch it to be of this form, in a way such that you do it non-adiabatically, in other words, you do not give enough time for the ground state to get adjusted, then you are going to be in this scenario where the potential well has changed, but the wave function for the ground state or wave function for this particular state, it remains the same as before. So now what is interesting is that this particular state, it is no longer the ground state of this new potential well because the shape of the well has changed. So in particular, this particular state, it's really a combination of the new ground state and the new excited states. In other words, what has happened is that because of this non-adiabatic change, you would say that excited states have appeared in the system. In other words, there has been particle production. So this is just a cartoon, but basically it turns out that in the context of cosmology, you can basically carry out this analysis and you can more technically do some Bogoliubov type computations to compute how many particles are produced. But the basic idea is still same as before. You have a particle mass that is changing with time, and that basically corresponds to particle production because the vacuum state is changing. So one can compute the probability of particle production. So I'm not going to get into too much details, but this is basically the expression you have in terms of this parameter M0 G that I was talking about. And the point here, this exponential factor that appears, that makes intuitive sense, because if you send M0 to be much larger than this kinetic energy scale, it says that the probability of production is exponentially suppressed, which basically means that you do not have enough energy in the inflating background to produce these particles efficiently. So you pay an exponential suppression. So that is basically just the probability of particle production. And then with that in mind, you can also compute, for example, the number density of these particles just by integrating over the phase space. So the broad summary here is that as long as M0 is not too far above this kinetic energy scale, you do produce a sufficient number of particles. You still can pay some exponential suppression, but depending on the precise value of M0, that exponential suppression need not be too large. So now coming back to your dark matter question, the analysis really depends on how small or large this exponential is compared to the scale of phi 0 dot.
But coming back to your point that this way one solves the overclosure problem, well, it's clear it will be the price of doing some fine tuning, right? Because it should be order 1 and it's exponentially dependent on these things, so it's very easy to predict much more than 1. So.
Yeah, that's true. Yeah. But people have, yeah, I mean, there have been papers like, for example, the Wimzilla and so on, where people have, yeah, these ideas, yes. Okay, so that was just some aspects of cosmological particle production. So let's now come back to the question of what these particles do after they're getting produced. So I'm going to be pretty qualitative on this slide, and I'm going to have some more equations in one of the following slides, but this is just to give the basic picture. So what's going to happen is that after these particles are produced, because there is this coupling G between the phi and the chi field, these particles, they can basically exert a force on the inflaton field. And what that will do is that because of that force, it can slow the inflaton field down. In other words, what's going to happen is that there will be some random locations in the universe where you produce these particles, and in those locations, the produced particles would slow the inflaton down, and that would mean that inflation would end later than when it was supposed to end. In other words, there will be a time delay as a function of the locations in certain random locations across the universe. But we also know that if we have single clock inflation, then any such time delay, it effectively corresponds to some curvature perturbation. In other words, wherever you have these particles getting produced, there will be some localized curvature perturbations around their locations. So I'm just drawing a cartoon here. So for example, let's imagine that space is plotted in this direction and you're just plotting gravitational potential as a function of space. And let's say here is a location where a heavy particle was produced. So what's going to happen is that just around this location, there will be a curvature perturbation, or in other words, there will be a gravitational potential that is localized around this location. So if you move too far away from this point, the gravitational potential would be, let's say, vanishingly small, but then around here, there will be a dip. So I'm gonna make this more precise in a few slides with some equations, but this is the basic cartoon level idea.
But when you say curvature perturbations, do you mean it's just colloquial term, or you mean that it's really not a diabatic mode?
This is really the zeta, the adiabatic mode.
It is a diabatic,
Yes.
so in that sense, it's not curvature perturbation kind of thing.
Yeah, that's right. So I'm gonna show you some equations in that. So what's gonna happen after this? These perturbations, they're gonna survive. Basically, it's the usual story. The modes, they will exit the horizon, they will remain frozen in time, they will re-enter back and then evolve. But what will happen is that after inflation, let's say the universe is filled with some thermal plasma, and you have these pockets where there are gravitational potentials that are being developed. So these pockets, they're going to trap more plasma compared to the surrounding locations. And as a result, when CMB is decoupled, these regions, they're going to emit more photons compared to their neighboring regions. So for example, if you imagine looking at the sky, then for example, let's say Planck is looking at the sky, when it looks at these regions, it's going to see an unusual number of photons, but then when it moves over here, it's just going to get more photons because more plasma was trapped in here. And again, when it looks in this direction, it's going to see the usual number of photons. So the picture is that there will be certain locations on the sky where the CMB would appear brighter than usual. And that's the phenomenology we want to look for. Yeah.
This might be a dumb question. Why look for changes in brightness and not like additional temperature?
So it's really the additional temperature anisotropy. So that's what I mean. You'll just see more photons coming in.
So I guess I'm a little confused then. If you have an overdense region and the photons need to go redshift, so won't you get a cold spot?
Yeah, good question. So I'm going to come back to that. So it really depends on, as you know, like for the CMB, the story is if you're focusing on very large scale modes, then you have this compensating effect. So you have to pay a lot of price to climb out of the webs and you effectively get cold spots. But if you go to sufficiently smaller case, that's not true. So I'm gonna have a plot showing that effect in a moment. Okay, so just very qualitatively, what I've shown you so far is that super heavy particles with masses much bigger than the inflationary Hubble scale, they can get produced during inflation, and they can lead to localized bright spots or hotspots on the CMB. All right, so let's now look into a bit more detail regarding what kind of properties would these hotspots have. We can look at, for example, their brightness, their numbers, their shapes, and so on. Okay, so let's try to make some estimate of regarding how bright these hotspots would be. So for that purpose, we can write down, so what you basically want to do is to understand to what extent a very massive particle creates a dent in the spacetime. So we can write down the action for a generic heavy particle. So m is the mass of this heavy particle, g is the coordinate time, and this is just the metric factor. Now, using just the Einstein equations, you can solve for g00 in terms of the curvature perturbation that sits in the spatial part of the metric. Okay? And if you do that, and if you plug back the expression of g00, you'd find that there is the familiar leading order term that we normally keep. This is just m times t, just the standard action. But then there's a correction to it coming from this factor of zeta. And what this tells us is that anytime a particle has a time-dependent mass, you get a non-trivial correction to zeta, and you get basically it's something like a tadpole term in the action. Note that if m were completely constant, then this term would not have mattered because it's just a total derivative. But in our scenario, we do have a time-dependent mass, and that's why this effect is important. So, along with this part of the action, we also, of course, have the standard kinetic term for the inflaton. So this is the kinetic term. It looks a bit funny because I'm writing the inflaton fluctuations in terms of the curvature fluctuation. So that's why there is some overall normalization factor. But it's really the standard kinetic term. So just to estimate how much zeta you get corresponding to this massive particle, you can just set all the derivatives. You can replace all the derivatives by Hubble scale just to get an estimate, because like Hubble is the natural energy scale during inflation, so that is sufficient. So this replacement is sufficient to give you a correct estimate. And if you then extremize the action, you would find like there is basically a linear term and a quadratic term, so you can just balance them, and you can find that the curvature perturbation corresponding to a massive particle, it has this particular dependence. So what is at least intuitive is that the heavier the particle mass is, the larger the curvature perturbation, which intuitively makes sense because the heavier particle would back react on the space-time to a larger extent compared to a lighter particle. Now this is a very, very qualitative discussion, but to do it more properly, you can do some in computation in inflation, and you can compute the 1-point correlation function of zeta, and you would see the same parametric dependence. Now normally such a 1-point correlation function would have vanished, but here we have we basically have a breaking of translation invariance because we have some random locations where there are hotspots. Okay, so this is the curvature perturbation that you get corresponding to this massive particles. Now, of course, this is not the end of the story because we do have the standard vacuum fluctuations that are generated during inflation. So these are just coming from fluctuations of the inflaton, and if you again drop factors of 2's and pi's, you can just show that basically the root mean square fluctuations that you get from inflation, it basically goes as this parameter. So this is again the quantity that is supposed to be like few times 10 to the minus 5, but again I have taken off factors of 2's and pi's, so it appears a bit big. So now what we can do is we can form the ratio between the curvature perturbation caused by the massive particle and the quantum mechanical fluctuations you get from standard inflation. If you do that, and if you rewrite the effective mass of the chi particle in terms of the parameters that we have in our theory, you'd find a very simple relation. You'd find that the ratio of the two zetas, they're just controlled by this parameter g. Okay? And just to recall, g is the coupling that basically appears in the Lagrangian, so you have a g phi square chi square term in the Lagrangian. Yeah.
So if this kind of ratio only depends on the coupling, so why do you only consider the heavy particle rather than light particle?
Yeah, so if you look at the effective mass of this particle, it's really g times this factor, and this factor is a very large number. It's like 10 to the 3 times.
Yeah, but why? I mean, but these all cancel. I mean, the mass of the particles are not.
Yeah. So this is So good. So the point is, it's really so you can say it in different ways, right? So this is just a particular type of parameterization. So all I'm saying is that if you have order 1 values of g, then you naturally have very massive particle.
Oh, okay.
In other words, if you had the mass to be very small to begin with, that would correspond to a very small value of g.
Oh.
Can I ask something? Maybe it's wrong, but if that ratio is further 1, then why can I trust any semi-classical calculation? I mean, if the quantum fluctuations are big, I would expect at least to not have only the zero mode of any field. They would have like a true tower of states with different momenta to do an analysis.
Good. So yeah, I should clarify. These are just the quantum mechanical fluctuations of the inflaton field. And what I was evaluating here, they are just the classical imprints of these very massive particles. So I'm really comparing two different sources of curvature perturbation. It's not like I'm trying to compute the classical effects of the inflaton itself with the quantum mechanical effects of the inflaton itself. They're really coming from two different sources. The reason I want to compare, because once we look at the CMB, of course we are going to have the standard CMB fluctuations, but then on top of that we are going to have these hotspots. So that's why we want to compare them. All right, so the summary here is that this is the coupling that basically tells you to what extent these curvature perturbations produced by this massive particle, to what extent they are visible over the standard quantum mechanical fluctuations. And we see, like, for order 1 values of the coupling G, they, like the heavy particle contribution, they can compete against the quantum mechanical perturbation.
Just have a question here. So people compute, for example, including you, environment inflation, right? Compute friction on the inflaton from particle production.
Right.
If you produce many particles.
Yes.
Right. So here you produce one particle, and you're computing now the delay and the exit of inflation from the classical potential law.
Yes.
But is there a separate kind of friction-related term from that single particle you produced, or is that really double counting this classical computation that we have?
Right. So we can take into account the amount of, if you want, the dissipation that the inflaton field have.
Yeah.
And basically, so I'm going to have a plot for that later on. But the summary is that you can work in a regime where the dissipation is very, very small, so you do not lose a lot of energy from the inflaton in production of these particles. But still, once these particles they are produced, they can just operate on their own and create density.
But there is an additional effect that you have not shown us.
Yes,
yet.
because that is just because it is subtotal. So in the limit, like, it really depends quite sensitively on this parameter m0, in the sense that if you reduce m0 so that the exponential suppression is no longer there, that's really a place where you produce tons of these particles. They will have their own effect, but before that, they can also slow the inflaton down sufficiently. Yes?
Should I think of this data particle as Gaussian distributed or not at all? Correlated with?
Yeah, they would be just Poisson distributed. So
Poisson distributed.
yes, yeah.
So they're uncorrelated also.
Yes. So they would be, yeah, they're just so what we are gonna imagine from the perspective of CMB maps is that, so we have so let me come back to that. We're gonna show some random distribution of these particles. So, but what we are gonna assume is that within each Hubble patch there might be some correlation in production of these particles. But if you look at the sky today, there are going to be many such Hubble patches, and these different Hubble patches, they are going to be completely uncorrelated. All right, so now let's come back to the question of what we actually see on the CMB. So again, the story is we have to understand the fact that these modes, they exit the horizon during inflation, and then eventually during radiation-dominated era, say, they come back in and they undergo various sub-horizon evolution. And that is something you can compute. There are, like, you can compute the Sachs-Wolf effect, the integrated Sachs-Wolf effect, the Doppler effect, and so on. And that we have done numerically over here, and I'm just showing the final result. So the summary is that corresponding to each massive particle, you basically would produce some circular-like structure on the CMB sky just because of spherical symmetry. However, the central temperature of such a spot would vary quite significantly depending on when you produce these particles. Okay, so that's what I'm plotting here. So eta star is the size of the co-moving horizon during particle production. And we see, like, depending on whether eta star is small versus large, the central temperature, which I'm showing in green, it varies quite a lot. In particular, if you focus on eta star being very large, which means you're basically looking at very large scale modes, you see that the delta T, it is actually negative. So this is when you would have cold spots. On the other hand, if you consider small scale modes corresponding, let's say 100 megaparsec or so, you'll have a positive delta T, which would give rise to hotspots on the CMB sky. But roughly speaking, the broad idea is that with order 1 values of the coupling, you can have the central temperature of these spots to be in the range of like tenths of microkelvin, which is roughly the average size of CMB temperature anisotropies. So this just confirming the fact that with order 1 values of the coupling, we have similar size anisotropies coming from the heavy particles when you compare them to the standard CMB situations. Okay, so now let's take a look at how these hotspots would look like and how are they distributed typically on the sky. So one useful information here is that just to conserve momentum, you would typically produce these particles in pairs. So you expect to have two such hotspots close by. The separation between these two hotspots, that really depends on the time of particle production. And what we assume is that given the time of particle production, which is determined by this eta star quantity, we basically construct the horizon size at that moment, and we randomly distribute these two particles that form a pair within that horizon size. So this separation here, we take it to be a random variable, and the separation can be anywhere between 0 and eta star. So that is just to simplify the model. Okay, so now let's look at how these things might look like. So this is the case for eta star of 160 megaparsec, and I have drawn again two such hotspots which are close by, and we see like they basically have like a core region which is pretty bright, and then as you move outwards, the temperature falls. If you do the case for, if you look at the case for eta star corresponding to 50 megaparsec, the profile changes quite a lot. In particular, it turns out that the hotspot, they have basically a ring-like structure. So you have some central bright regions, but then the temperature falls a bit, it becomes a little bit cool, and then again it picks up. So these complicated effects, they are just coming from different transfer functions that that the associated modes go through, because an eta star of 160 megaparsec modes enters at a different time into the horizon compared to an eta star of 50. Okay. So these are just some sub-horizon effects that one can take into account. All right, so finally, we can also compute how many of these things you expect on the sky. And for that purpose, we can just look at the expression for the number density that we had before, and we can just apply a standard dilution factor. So if these particles were produced at, let's say, when the scale factor was A star, we can just do a standard dilution, and then we can compute, we can take a given volume and multiply the number density by the volume to get the total number of these hotspots. So for this volume, what we assume is that given that this is the CMB surface, we basically consider a shell that has a width of like delta eta, and we basically count how many of these hotspots can lie on the shell. And the point is, these hotspots, they need not be exactly on the surface to give an effect. They can be slightly off the surface as well, and even then they can still perturb the CMB temperature fluctuation. So that's why we are considering the shell. Now, just to give you some numbers, if you, for example, take this value of the minimum mass M0, this to be the size of the spot on the sky. So this is a pretty big hotspot. It has a size of like 100 megaparsec, and a value of coupling which is like 3. You typically get like order 25 of these hotspots distributed across the entire sky. And this,
yeah, can you explain a little bit this momentum conservation? Because well, particle may have zero momentum, right? It can be almost literally in the spherical wave. Because naively one pays in the exponent twice the price for producing pairs of them. So
yeah, so I'm assuming that you so I'm assuming that you always produce something which is very soft. I mean, it can be very close to 0, but it is just some non-zero momentum that the particle comes out with. Because it's basically production from vacuum, and you do not have any momentum in the initial state, so you just produce 2 of them which are back to back.
some probability of getting something that's sufficiently zero momentum versus the
Yeah,
price
basically
you pay.
because it can be almost at rest, right?
Yeah, so let me
And there is exponential price to produce two of them, so it's not.
It's not obvious that you win one way or the other.
Right. Yeah.
so let me get back to this this aspect here. So this is the probability for particle production. So this Kp here, that's the physical momentum of the particles that are produced. So you are already paying this price coming from the rest mass itself. So it does not cost a lot to produce a very soft mode, which is basically like a non-relativistic production, if you want.
But then why do we produce two of them?
So I mean, if you produce one that has some momentum, you'd have to like balance.
No, he's saying why not just, if there's no other conserved number, why not just produce one that's like at rest within whatever requirement of being zero momentum? I mean, there's very small phase space presumably to produce that.
Because presumably, okay,
But
there's some uncertainty because it's within Hubble
Right,
scale, so
yeah,
it doesn't make sense to talk about momentum softer than Hubble, right? So
that's kind of the job. But you only produce one of them, so you would not take as hard a hit in your exponential.
Right. So I think Kp equals 0. That's definitely a possibility, but it's just one point in the phase space. So what I'm saying here is that there is a part of phase space where Kp is sufficiently smaller than m0, so you can still produce like pairs without paying.
But I think what he's saying is that that's the probability to produce two, right?
Yeah.
And he's saying there should be a separate probability which is not as exponentially expressed, but still exponentially expressed to produce one, where Kp is 0 within the uncertainty of the.
Right. So I think just by the exponential, I think that is a possibility that you can just produce one. But then if you were to do the computation in this particular model that we are considering, you always have like a chi-square, chi-square type term. So in other words, you can put a Z2 on chi so that a single production is just
another conserved number.
Yeah,
than
that I
the-
understand. Yeah, there's
yeah. So I think I think for example, if you had a chi cube term, you could have a scenario where you produce only 3, for example, and so on and so forth. But then, so that part might be just specific to this particular model. All right. So okay, so let me just summarize this part. So, so what I've seen is that there are basically 3 parameters. The parameter G that controls the central temperature, and we have seen like order 1 values of G would basically give you similar temperature perturbations as in the CMB, as in the standard CMB fluctuations. There is also this parameter eta star, which is basically something that governs the sizes of these spots and how they look like on the sky. And finally, this is the parameter that controls the exponential, so it determines how many of these hotspots you actually produce in the sky. All right, so in the remaining like 10ish minutes, let me very briefly talk about some of the sort of strategies you can adopt to look for these things. So I should clarify that we have a couple of sort of strategies in mind. The first one is very simple. It's motivated by basically collider physics analogies. And the second one is based on machine learning tools. So I think because of lack of time, let me just talk about the first one. It's because it's very simple to motivate. And then if you're interested, I can chat more about the CNN aspect later. Okay, so basically this is an image recognition problem. We want to understand very faint hotspots we want to basically dig up very faint hotspots from CMB maps. And here I'm just showing 2 images of small patches of CMB, and one of them contains hotspots, the other one does not. And if you look at closely, because we have simulated these images ourselves, we would know like this is the guy that contains the hotspots. In particular, we have injected 3 pairs of hotspots on particular locations on the sky, and here is how they would appear along with the standard CMB fluctuations. But this basically illustrates the challenges for doing these searches, because if you have order 1 values of these couplings, these spots, they are not extremely bright, so they need not stand out very strikingly when you look at the CMB.
It's odd though, there seems to be small scale structure in the left one that's not in the right, that's not associated with the hotspot. It just looks grainier. Is there something
Yeah, maybe.
about my eyes that's failing?
Yeah, I'm not totally sure because we literally took the same map. It might be something to do with the color. But you're right. I see what you mean.
Right, yeah.
It's not, I guess mine is 400.
Yeah.
Oh, wait,
Yeah.
yeah, yours is slightly different. Okay, sorry. I was reading it too fast.
Mathematical automatically adjusts the scale.
Scale is different.
That's true. That's true.
Yellow is 400
That's
on
true,
the
that's
left
true.
and
Yeah,
450
yeah,
on the right.
Yeah.
That's true. That's true. Yeah. Okay. So so what you can do is like the
Very
first
good
thing you can the first thing you can do is something actually very simple, which is to say that if you have these hotspots lying around, the CMB would just be hotter than usual. So it's a very naive and simple statement. And the way you can quantify this is that you can ask, if you put a cut on the temperature, how many pixels would survive if it was only the CMB that we were seeing in the absence of any hotspots. So what you can do is that you can again take the maps that are showing and you can put a cut on the temperatures of the pixels. And if you have only the CMB, you will see still certain pixels surviving. But if you have the hotspots, you will see, of course, additional pixels surviving. And of course, the temperature of these hotspots and the choice of the temperature cut, they're important. And if you put a very stringent cut, of course, nothing is going to survive. But this is just to give a basic idea of how one can design such a search. And then you can define some significance measure. Basically, this is just doing some S over root b type analysis in terms of knowing whether there are excess signatures on the sky or not. So I'm not going to go into the details of the expressions because they're not super illuminating, but this is the result that we have. So what I'm plotting here is how many hotspots you can hide on the CMB sky as a function of the coupling. And we actually, although I'm plotting straight lines here, we actually took just 3 data points, like g equals 2, 3, and 6, just as example benchmarks. So what we see is that at 2 sigma, one can hide, for example, for g equals 3, one can hide like order 400 of these hotspots. And then, keeping that value in mind, you can actually ask another question, which is, so far I've been talking about position space searches. I've been talking about CMB maps and how we can put temperature cuts to analyze or to look for these hotspots. But you can ask to what extent these hotspots affect the CMB power spectrum itself. And that is something we did over here. So we took the benchmark of g equals 6 and the number being 16, which corresponds to this value over here. So from the position space search, you would say at 1 sigma, you can hide these many hotspots. But then if you were to inject these many hotspots on the map and do the reverse Fourier transform, you will see that the power spectrum, the CMB power spectrum, would be very similar to the case where you do not have any hotspots. So blue would be just the standard lambda CDM prediction, and it is almost identical to the power spectrum that you get if you have hotspots. So that's why the red and the blue, they're almost overlapping. There is a small degree of residual here, but that is inside the error bands that we have.
Could you explain what exactly you mean by hiding these spots?
Right. So what I mean is, so if you inject too many of these spots, you will start noticing that there are more surviving pixels compared to the standard lambda CDM prediction. So if you
select a certain temperature.
Yes. So you can optimize for the temperature cut, and then once you fix a temperature cut, so corresponding to each temperature cut, you would have a number for lambda CDM, right? Because you can just simulate lambda CDM. So that's what we do.
So in some sense here, you're using the one-point distribution function of, you know that the CMB is Gaussian.
Yes.
So could you also use non-Gaussian searches for non-Gaussianity in general to get a more sensitive?
Yeah. We can definitely do that. So so this is something that we did not carry out in this particular paper, but one thing what one can do is to compute the non-Gaussianity shapes that you have for these particle productions, And one thing that we found is that like this would be non-Gaussianity, which would be peaking around eta star. It would be peaking around certain scales. And I am at least not aware of non-Gaussianity searches that basically select out particular scales. So that's something I'm very interested in if the non-Gaussianity searches are powerful. But if you just look at like local non-Gaussianity searches or more standard searches, then that would not be super sensitive because the signal is really peaking at a certain scale.
But if you just made the Fisher estimate of how sensitive, not using the current searches, but if you were to build your own search,
right,
more sensitive than this cutoff method?
Yeah, so that's an interesting question, and I do not know the answer whether that would be more sensitive or not. So there is, I don't have a citation to that paper here, but there is a paper by Kendrick Smith and Moritz Muntner, who basically looked at endpoint searches more generally in the presence of particle production. But I think it's a bit difficult to compare one-to-one just because some of their couplings were very, very large, like much larger than one. So we're not exactly sure how to map that out. But yeah, this is something I'm very much interested in. So yeah, for sure, like non-Gaussian researchers can also be part of it.
Something. So
yeah,
16 is the amount of these massive particles that are created in the entire universe. Like
on the entire sky. On the entire sky.
The entire sky.
So if you recall, like we have this shell around the CMB. So if these particles, if they are distributed, for example, too close to us, they just won't affect the CMB sufficiently. So they need to be within the, basically within the, if you want the CMB surface, like it has a certain thickness. So you can compute these effects. Like you can, like if we are the observer here, you can compute the temperature anisotropy dependent on, that depends on the location of these particles. That's all. So yeah, so the numbers that we mean, they're really the number on the CMB.
How would we show up a large scale structure?
Yeah, so that's a very good question. So we are currently thinking about it. It's a very challenging question in the sense like so maybe for large scale structure you might have some power, but naively I would guess if you're looking at sufficiently large values of eta star, CMB is likely more powerful.
But wouldn't you expect to see, for instance, just because you basically are getting extra fluctuations in specific spots, those kind of get a head start in their growth. So you would expect to see, for instance, like if you want to be like really optimistic, there's these people talking about these like really massive galaxies that form too early.
That's true. We have not thought about it. Yeah.
You kind of get
you
got unreasonably lucky to have gotten them.
Right.
And here you would have been like, well, that's just where you got this extra factor of 2 in curvature where you started, so you didn't have to grow for as long.
That's true.
So is there effect on CMB from propagation, something like cleansing of CMB by these hotspots, kind of, which are in the volume, in the volume?
I guess they're, I'm not sure how strong the lensing would be because I mean, if you want like the curvature perturbations corresponding to these hotspots, they're still like 1 part in 10 to the 5, like for order 1 values of the coupling. But maybe if the structures grow sufficiently,
then they will grow.
But they all eventually become nonlinear, right? It's just that if you looked at a particular redshift, you might see some objects that were unreasonably got them collapsed unreasonably earlier.
Yeah, that's true.
That's why I'd be more like looking at the tails rather than some sort of statistical average.
Early or late? Because these hotspots, they correspond to the regions which were inflaton and reheated later. So it doesn't get keep.
So I guess it depends just on the eta star value, like when these modes re-enter the horizon. I guess that's what you mean.
Well, I mean, the scale will correspond to when they entered the.
But yeah, for large scale structures, do you get over densities in the matter
in
the matter, or do you get under densities? You showed us for photons.
Right. Yeah, we don't know. We have not evaluated things. Yeah, it's a good question.
Because you had longer, you diluted more. So the fact that you have less time means that you
Right,
get
so you have
less.
less of redshift of
Yeah,
there, and
so
that's,
you end up being over density.
that should be over, yeah, that's always very interesting to know.
Yes. Okay. So let me just conclude over here. So the next part was more about using the precise profiles, like the angular profiles of these hotspots, and you can utilize that to develop a machine learning search based on CNNs. But let me just skip over all of that and summarize here. So hopefully I've told you that very heavy particles, they can get produced during inflation. They would lead to hotspots on the CMB, and either this cut and count search or more powerfully the machine learning search, they can detect like order 10 of these hotspots distributed across the sky. There are various interesting steps that you can do. So for, of course, the galaxy surveys, they're interesting. And then one can also potentially do an actual search with the Planck data to look for the spots. So yeah, with that, let me conclude, and thanks for attention. Yeah.
Maybe a naive question, but is each one of these hotspots produced by one single particle?
Yes.
So one single particle of 14 GeV can lead to something relatively similar.
Yeah, so what happens is that it does have it's not microscopic, it does have a size, and the idea is that if you produce this massive particle, it like creates this dent in space-time, and the size of this thing would like it can basically affect the space-time in a causal way. So you can compute the size of the horizon at the time of particle production, and you would find like basically affects all of the space-time in that location. So you can, for example, compute. You can, for example, compute how these things look like as you move from the center of these hotspots. You can compute the profile. So they always have a certain thickness or a certain shape or a certain size rather associated with them, and that size roughly corresponds to eta star as well.
And how do you distinguish this effect from generic non-Gaussianities?
You mean primordial non-Gaussianities, or
Yeah.
yeah. So I think that's what that's what we were also discussing earlier. So I think the main effect, because you always have a certain time scale when particles are getting produced. So if you were just to look at endpoint correlation functions, you would see an enhancement on certain scales. So I'm not sure how to, like, I think most of the non-Gaussian searches, they typically assume some sort of scaling variance, if you want. Like, they look at multiple, like the signal is often spread across various values of k. So I think directly applying those searches is going to be tricky, but then you have to devise something that is more specific to localized signatures. So yeah, I'm not sure what is, in some sense, the best way of looking for these things using non-Gaussianity, but I think that's a very interesting question.
And we assume that this doesn't interact with anything else, right? I mean, that
Right.
this big mass doesn't decay on anything. Like,
Right,
there's
so-
no reason why the chi will go into a phi again.
That's right. So what's going to happen? So it's if you want, once these particles are produced, they're just leaving their imprint on the metric fluctuation. So they need not decay into any other standard model particles, for example. Like even if they were to decay into some standard model, you'll still see this, if you want, like over dense regions which are kind of localized.
Do you have a projection of CMB support?
No. But I mean, roughly speaking, so I mean, it's a, yeah, so it depends, like whatever we were, so let me go over here. Yeah, over here. So for our benchmarks, we basically focus on values of eta star, which are of the order of like 100 megaparsec. So that corresponds to like L modes of 100 or so. And in that range, you already have very good precision from Planck. So CMBS4 would be relevant, for example, if you were to go to very large values of L, so very small values of eta star.
The delta T over T divided by delta T over T, the delta T over T that you predict divided by the delta T over T that you would expect in the CMB to make something which you're saying is detectable has to be how big?
So that just is governed by this number
Well,
G.
I know G is
Yeah.
what sets it
Right,
to
right.
be detectable.
To be detectable, I think you typically, so let me see if I have a, yeah, so let me just read it off from this plot. So we, for detections, we find that especially using the machine learning analysis, you can go to even values of G of order 2. So then you are looking at core temperatures which are like 80 microkelvin. And that by itself, like CMB, of course, it has acoustic oscillations. So the temperature is not the exact same thing at all different scales. But that is like one example value to keep in mind.
True, interesting. Because naively, I would have said that if the fluctuation were the same size, then that would look like a rare 1 sigma fluctuation, right?
Yeah. Mm-hmm.
And so rare 1 sigma fluctuation, I would not have thought would be, but a rare 2 sigma fluctuation would be more detectable on a rare 3 sigma. That rare if the G is basically telling me how big in terms of sigma, in terms of the size of the fluctuations that I see, and then you're telling me separately how many of them I have, then I can ask, like, is that more or less than I would have expected to have already seen in the CMB, right?
Right. So what I'm saying is that for each value of G, you'd also have to give the associated number for these, for like how many of these.
Right.
Yeah.
Yeah.
So if you, for example, had just like one such spot, that is not enough to. Like,
unless G was 10.
Unless G was like 10. Yes.
And then it would.
Yeah.
I'm not sure if this is the right way to think about it, but if you go back to the picture where you had the delta eta, you were showing a shell that you consider around the CMB surface.
Okay. Mm-hmm.
So you mentioned briefly that the distance of where the particles are produced from the CMB surface can also vary the brightness of the hotspot.
Yeah.
Is there like a degeneracy between G and the distance?
Yeah, so that's a good question. So in some sense, yes. So I do have a, let me. So yeah, here's one plot that basically looks at how much temperature anisotropy you get as a function of the location. So this is the line that corresponds to the basically the CMB surface. And if you move away from these lines, you see, of course, like the temperature anisotropy that is falling. So if the hotspot or if the massive particle generated perturbation, if it is very far away from the CMB, it does not affect the CMB line. So yeah, you are right that in principle there is a degeneracy. So what we do in our study is basically to distribute the hotspots in a random fashion within some shell, and then keep G as the varying parameter. So if you want, like we marginalize over this effect in terms of the location of this massive particle.
Okay. Let's thank Soubhik again. You'll be around this week.
I'll be around all of next week, but I'm going to Stony Brook in the evening, like I have talked there next.
All right. Thank you, Soubhik.
Yeah. Thank you.